Hi, this is Mr. McConnelly. This is BKW Physics. And yesterday we jumped right into the idea of adding vectors. And vectors could be added end to end, or they could be added at angles. And what we worked on yesterday is, as long as we drew them to scale with the proper magnitude and the proper direction, because those are the two key things that you need with vectors, we could get a diagram or an answer that was reasonably accurate and correct. But today we're going to take it one step further. We're going to hit the math end of things. So I'm going to start with this problem here. In this problem, I did not draw this to scale. I just labeled it so you could hopefully see the numbers and see that it's maybe close to accurate. And in this diagram, these two vectors, one pointing up at 110 newtons and one pointing to the right at 55 newtons, meet at a 90-degree angle. Now you can imagine a scenario where maybe this is two people and they're pulling on a rock or something. Or it could be a crate or something to that effect. Basically you have two people and one person is pulling that way and one person is pulling that way. Now, in your mind, before we even start the problem, if two people are pulling and this person is obviously pulling harder, which way is the crate going to move? You kind of point with your hand right now. Okay? So some people are pointing straight up and some people are pointing more this way. And the people that are pointing more this way are correct. Because this is not the only person pulling. There's also this person pulling. So when you combine the two, it's going to kind of move in this direction. Okay, fine. Well, what do we have to do to really solve this problem? Well, the first thing we have to do is realize that these two vectors are added tail to tail. And you know from yesterday's lesson that that is not the way you add vectors. How are vectors added? Vectors are added tip to tail. The tip of one needs to be connected to the tail of the next one. Tip to tail is what we say. So, all right, let's say then we decide, well, the 110 is really not in the right spot. Let's move the 110 over here, and I'll move it in blue so you can differentiate it between the first 110. So now I have the 55 meeting up right there to the tail of the 110. Good, I have them arranged in a proper orientation. Now, if I drew them that way, where would the resultant be of this diagram? The resultant is always from where I started to where I. Okay. So I started down here, and I ended up there. This is now my resultant. So for all intents and purposes, I'm ignoring the green 110 at this point. I'm just looking at the 55 to 110 and the resultant, the green, blue, red triangle. And what do you know about this triangle? Well, it is a right triangle. And that makes things kind of handy. So, the process of actually solving what the resultant is. Let's think about our math concepts. We can use a squared plus b squared equals c squared. First step is always write our equation. Step 2, we plug in our numbers. And I hope some people are following along with their calculators so that I can give you some numbers in a moment. 55 squared plus 110 squared equals c squared. When we square each one of those, add them together and solve for c. Can someone give me an answer on that? Nope. Joe, can you try again? Oh, that sounds better. Alright, Joe sees his mistake, not a problem. And so it's somewhere around 123, you said?
Yep.
Okay, 123 newtons. So our resultant, switch to my red marker, is 123 newtons. But that's just the magnitude of it, and resultants always need a direction. And how do I go about finding a direction? Well, when I'm looking for the direction, what I'm really looking for, in this case, is this theta right here, this angle right there of that triangle. And the easiest way to do it is to use the idea of tangent of theta equals equals opposite side over adjacent side. It's the concept you cover in math. Let's plug in some numbers. So the tangent of theta is equal to, now opposite means opposite the angle, so I go straight across. And straight across is the 110 newtons. And the adjacent is your next door neighbor, but it can't be the hypotenuse. It's just got to be the next door neighbor that's not the hypotenuse. So the next door neighbor is the 55. So we divide these on our calculator and we do a tangent, second function tangent of each side, second function tangent of each side. Anyway, what does it give us for an angle? Someone follow along? What'd you say, Ashley?
63 degrees.
I agree with that, 63 degrees. So now we can say that this resultant, bottom line, therefore, if you like the math terminology, therefore the resultant is 123 newtons at 63 degrees. Beautiful. But there's someone that's thinking right now, hold on, back it up, back it up, back it up. Go way back to the beginning. I know we decided to move the 110 over here, but that's not how I was going to do it. I was going to move the 55 up there. And that's still tip to tail, right? So is this a legal way to add these two vectors together? Yes. Well, we better do the problem again because this looks totally different, and I'm not sure it's going to come out right. So let's quickly go through it again. So now tip to tail, where did I start? Well, I still started there. Where did I end? There. So my resultant, I can see visually, I can see that that's the same resultant. So if I do a squared plus b squared equals c squared, I'm still going to get 123, correct? You with me? But I got one problem here. What about when I solve for that angle? Is that going to give me 63 degrees? No. It's not. Let's do it. Let's see what it gives us. Let's do the tangent of theta is equal to the opposite, which is now the 55, over the 110, which is the adjacent, opposite over adjacent. So go ahead, someone on the calculator, give me that number.
25.
25, you said?
No, I said 27.
27? Yeah, that sounds right. That sounds right. So now the angle comes out to be 27 degrees. Huh. Which one of these is right, the 27 or the 63? And at this point, I got to back you up to what you learned in math a while ago. I'm going to shade in black here, trying to make it pretty dark so you can see. You remember in math you had a coordinate axis? And when you had a coordinate axis, this direction was called what number of degrees? 0. If you went straight up, you called that 90 degrees. If you went this way, it was 180 degrees. And if you went straight down, it's 360 degrees. So, if we're looking at my resultant right here, what direction is my resultant pointing? Is it pointing at the first theta we came up with, which was 63 degrees, or is it pointing at the second theta we came up with, which is 27 degrees? Is that direction 63 or is that direction 27? And I think most of you can see that resultant is 63, because if this is 0, you're up to 63 by the time you get to here. Okay? Now, if you had done the problem this way and got 27, all you would have had to do is you would have had to say, oh, yeah, that is 27 right there, but the actual direction of the resultant is 90 degrees minus 27, and then it would have come out to be your 63. Okay? Understood? So sometimes you got to look at your picture and reevaluate. All right, moving quickly to the next diagram. Well, sometimes you're faced with a scenario where they say something like, a person is pulling a crate across level ground. How much force is responsible for moving the crate forward? So force to move box forward. Question mark. So, and I gave you how hard the person was pulling on the rope. Notice the rope is at an angle. They have it over their shoulder and they're kind of pulling, forward. So, they're pulling with 150 newtons at a 45-degree angle. And I want to know how much force is responsible for pulling it forward. So this 150 I gave you, what is it? Well, break it down a little bit. How about if I did this for you? I made it into a right triangle. Can you see that that 150 is actually the resultant of this picture? Can you see that really, if you take the bottom one here, the force in the horizontal direction, we'll call it, because it's along the ground, and I make that a vector by putting an arrow, and then I come up this way and make that a vector, and we'll call that force vertical, that I have added the force horizontal tip to tail with the force vertical, and I get the resultant of 150 from where I started to where I ended up. You see how I just converted that picture from something that didn't look familiar to something that does look familiar? This is a common practice. You're going to do a lot of these sorts of problems. People pushing lawnmowers, people digging with a shovel, people yanking something upward at an angle. They're all the same type of problem. You just have to break it down this way. So kind of use this as a template. How do we finish it? Well, which one am I looking for? Force to move it forward, is it which one? Haley?
Or FM.
This one? Is that what you said? Yeah. Okay, so yeah, you're definitely looking for the bottom one. So how do we go about doing that? Well, I want that, I have an angle, I want that, and I have the hypotenuse. This is not really sine anymore, is it? I mean tangent anymore. And it's not sine, because sine would be opposite over hypotenuse. What is it when you have adjacent and hypotenuse? Which law is that? Yeah, cosine. So the cosine of theta is the adjacent one over the hypotenuse. Always write your equation first, without the number in it. Cosine of 45 degrees is the adjacent one, that's what I'm looking for, and I'm going to write it just as FH over the hypotenuse of 150. Do a little calculator magic and tell me what you get. So, you basically would take the cosine of 45 and multiply it by 150. What do you got, Howard?
106.
Yes, 106. Agree? Nice. So the force horizontal would be 106. Bottom line, what that means is if you were pulling on a rope at a 45-degree angle with 150 newtons, the part that was pulling you forward, the actual part that was moving you forward, is only 106. So you're wasting like 44 newtons worth of effort. Wasting, I don't know. But you can think of it that way, because it really only required 106, and if you had bent down and pulled the rope along the ground horizontally, you would have only had to pull with 106 instead of 150. But that would be awkward and uncomfortable, so most people would do it like that. So for today, physics.